All right, so this is the last topic of the review. So now we are looking at ocean acidification. So there are two main pathways that carbon enters the ocean, from the atmosphere into the ocean. So if you go back in part 4 and you look at a carbon cycle, this is just we looking kind of zoom in into the carbon cycle, right? Just the interaction between atmosphere and the ocean. So there's two ways. One is the physical way, where there's passive diffusion or exchange between carbon dioxide between the atmosphere and the ocean. And here you have a biological pathway where carbon dioxide gets absorbed by those organisms, organisms called phytoplanktons. And those phytoplanktons eventually they get eaten by bigger things, zooplanktons, and those zooplanktons eventually they get eaten by something bigger. Eventually they die, and the carcass gets deposited on the bottom of the ocean. And over a long period of time, they actually become part of the bedrock, and uh, and then eventually they make their way into become a sedimentary rock. The one thing I wanted to make sure that you understand here is that this absorption of carbon dioxide from the atmosphere does not contribute to ocean acidification. And the reason for that is because the carbon dioxide, they get photosynthesized into carbohydrates. So actually that becomes food for the organisms that live in there. So there is no carbonic acid being formed or hydrogen ions being released. So this pathway does not contribute to acidification. Okay, we have then the biological pump where carbon dioxide is absorbed in water, and then it triggers a set of reactions, which we'll talk about it in a moment. I just want to stay at the surface for a moment. So there is an exchange of carbon dioxide that comes in and out of the atmosphere, and it is under an equilibrium. Okay, so not all equilibriums need to be chemical equilibriums. This is in the cases of physical equilibrium, where carbon dioxide in an atmosphere, so it's in a form of gas, um, enters and leaves the ocean, which is carbon dioxide in aqueous. Right, so this is the first step in a physical pump process, is carbon dioxide entering and leaving the system. Just like with any reaction under equilibrium, it will it will be affected by temperature, right? And it will be affected also, and I should have put in here, by concentration. Okay, so looking at temperature, we talked about this before. We said that gases um, do not dissolve well in water if it's hot, right? So there is a inversely proportional relationship between heat and concentration of gases in that gets dissolved. The warmer it is, the less gases are dissolved. So if temperature increases, the amount of gases that gets dissolved is going to decrease. That is only at the surface, right? At the surface of the ocean. The game changes at the bottom because of there's a large amount of pressure. But just talking about the surface of the ocean, that's usually holds true for temperature. When we talk about concentration, and this is relevant to ocean acidification, when we talk about concentration here, we're talking about concentration of carbon dioxide in the atmosphere. So as we increase this, the equilibrium will shift this way towards more dissolved carbon dioxide. So that's where it all begins, right? Because once this carbon dioxide becomes aqueous, in other words, dissolved in solution or dissolved in the ocean, then it triggers a set of events. Let me clear this and go to the next slide. Okay, and this is the set of events that triggers. Carbon dioxide dissolved in water forms carbonic acid, and that carbonic acid dissociates into bicarbonate and this hydrogen ion. So this is where the acid comes in. Okay, so remember that pH is a measure of concentration of H. So this is the species that really is affecting pH. The other thing I want to notice, carbonic acid is a weak acid and is under reversible reaction in equilibrium. So this is a carbonate buffer. Okay? And because this is a buffer and is under equilibrium, is going to behave just like any reaction in equilibrium. temperature concentration will shift the equilibrium to the right or to the left to reestablish that equilibrium. Go back and look at the Le Chatelier's principle and how reactions shift to the right or to the left to reestablish the equilibrium or to counteract the stress. It's going to act the same way. So, a few ways for you to think about this. Putting this in the context of ocean acidification. So you have carbon dioxide entering through the physical pump, and it gets dissolved, and then it becomes carbonic acid. Okay. The carbonic acid further dissociates into this hydrogen ion. That's what's responsible for lowering the pH. So look at this: lower pH equals high H. Okay. So this could stay as it is. However, we are talking about buffers. Okay. So the reaction will shift this way in order to reestablish equilibrium. But there is another piece of this buffer that we haven't talked about yet. Carbonate, okay, will react with hydrogen, okay, with hydrogen ions to form bicarbonate. Okay, so the more hydrogen ions are present here, more carbonate will react. Okay, so this is part of the buffer as well. So that would lead to a decrease in carbonate here. Don't worry about this last part. This would lead to a decrease in carbonate here. One of the problems is that carbonate is not here just to be a buffer for acidification. It is also used by organisms to build shells. This is called calcification, right? So carbonate reacts with calcium to form calcium carbonate. You might wonder, where does this carbonate come from? Right, that's a legitimate question. Where does this carbonate comes from? Well, it so happens it comes from limestone. So when rocks and hills and whatever it is made out of limestone, when they weather, right, when they get eroded, eventually they'll wash. Okay, eventually they'll make their way into the ocean. I don't know if you guys remember, I mentioned this long time ago. If you're ever around Lime Ridge and it rains, the color of the water is slightly white. It's very milky, and that's because it has weather or has removed some carbonate from uh, from the rocks, and some lime as well, which is calcium hydroxide. But that eventually will make the way into the ocean. So that's where this carbonate comes from. And then another way for you to visualize this is by looking at this. This is a picture of this process, so the chemistry of the ocean in the late 1800s. And this is the projected chemistry of the ocean in a few years. So carbon dioxide enters. Notice that what they're really showing here is the pH, a drastic decrease in pH. Remember, pH is a log of 10, so small changes means a lot. But they're showing the arrows. Notice how the arrows changed. Okay, so that's what we're looking at. So carbon dioxide enters, becomes carbonic acid, releases some hydrogen ion. That's what's responsible for the pH. And then the hydrogen ion will react with the carbonate ions to form bicarbonate. Okay, but this, at least in this scenario, this is not a primary reaction. The really primary reaction is this carbonate is being used by corals, mollusks, and any marine calcifier will be using that, as well as a lot of animals like fish. They build their eggs using carbonate as well. Right, so it's key to the ecosystem, this carbonate here. So in this future projection, we still have carbon dioxide. Notice there's a lot more. Okay, so 1 versus 3, there's a lot more. Okay, so increasing concentration will shift the equilibrium this way. Right, remember the carbon dioxide is in equilibrium between atmospheric and ocean. So we'll push the equilibrium this way, which means that more carbonic acid is being generated, more hydronium ions are being generated. This now takes a huge role, right? This carbonate with hydrogen ions to form bicarbonate is taking a much bigger role. That means there's less carbonate available for the calcifiers, and that is one of the big issues. So the consequences of ocean acidification, well, it affects the entire marine ecosystem. It's not just the calcifiers, well, primarily or not primarily, directly the calcifiers, but it will affect everything else. And that's what it says here. Calcifying organisms, they will lack the building blocks, which is calcium carbonate or carbonate, but without carbonate, there's no calcium carbonate, right? It will alter the food chain because it's not just organisms. Those organisms, they eat and they're eaten by other things. Um, it will affect the marine, affects atmospheric composition. As we said before, a lot of those organisms, they're responsible for photosynthesis. So it will affect the composition there as well. And some indirect effect will be coral bleaching. The coral bleaching, though, is mainly due to increase in ocean temperature, which is unit 4, right? Climate change. But it will also is being aggravated by pH changes. And then the same can be said for algae blooms. Algae blooms, primarily, the primary driver of algae blooms or red tides are increasing fertilizers in our water. However, ocean acidification does not help. Okay, so that's what you need to think about. And then there's large economic and health consequences for humans. So that is the end.